is ionization energy? It is the energy required to remove an electron from a shell. Okay, so let's look at group 4 elements. Group 4 elements are both metals and non-metals. These group 4 elements are wonderfully made because they're a combination of metal and non-metal. They have dual oxidation states. Usually the oxidation states are between +2 and +4. While some elements are stable in +2, some other ones are stable in +4. Now, elements in this group 4 includes, you have your carbon, silicon. Now, these other ones are outside of your syllabus. These other ones are outside of your syllabus, but I just put it here for you to know. Silicon, you have your germanium, you have your tin, and you have your lead. So, silicon and the carbon, they are what? Non-metals. But tin and lead are metals. And this one is a metalloid. This is a metalloid. So that's why I said that group 4 is a wonderfully made element or a wonderfully made group. Okay, group 5. Group 5 are non-metals and they have dual valencies. They can either be 3 or 5. And elements found there include nitrogen and phosphorus. Then elements in group 6 they are non-metals, they are electron acceptors, and they are good oxidizing agents. These elements include oxygen, sulfur. Then you have elements in group 7. They are referred to as halogens because they are salt formers. They form salt. Halogens are salt formers. They are the most reactive non-metals. When you talk about the most reactive non-metal, you're looking at group 7 elements, the halogens. Unlike the metals, the most reactive is group 1, the alkali metals. Now, they are colored and they are the atomic molecules, and examples include fluorine, chlorine, bromine, iodine. Okay, so here are group 0 elements. These group 0 elements, they are known as rare or noble gases. They have no bonding electrons in their outermost shell. That is why they are unreactive. They are unreactive because they don't have any bonding electrons in the outermost shell. They have attained stability, the duplet or octet states for stability. So because of it, they are stable and they are unreactive or inert. Now, they are inert, just like some persons who don't socialize with other people. You say they are unreactive, they are inert. We have people like that in chemistry. So these noble gases, they are inert. They don't react. They don't talk with anybody in the periodic table. They're on their own. Then examples are helium, neon, argon. Other examples are xenon and radon. These two are radioactive. Then we look at the transition elements. Remember, the transition elements are found between the group 2 and group 3 elements. Now, these transition elements, I want us to know that they have what we call partially filled 3D orbitals. Partially filled 3D orbitals. They have partially filled 3D orbitals and they have variable valencies. Okay, it's already here. Partially filled 3D orbitals. They have complex ions. They have colored ions. They are colorful. And they have high tensile strength, including high melting points as well. Then we look at the elements in period 6, not group now. We are done with the group. The group ended in group 0. So we are looking at elements in period 6. We are looking at the lanthanides. Example of lanthanides is what? Cerium. This lanthanide is also known as rare earth metals. This lanthanide is also known as rare earth elements. Then period 7, we have the actinides or artificial elements. These are byproducts of radioactivity. They are byproducts of radioactivity. Example, thorium. Now I want you to know that elements in the transition elements, many of them are very good many of them serve as catalysts, like manganese, iron, copper, nickel, many of them serve as well. They are very good for commercial purposes. Okay, so let's look at this basic concept as it regards periodicity. Now, atomic size or ionic size, it decreases down the group due to increase in nuclear charge, which tends to pull the electron to itself. But across the period, it increases due to successive addition of shells. I want you to note that between atomic size and ionic size is bigger than ionic size. This simply refers to the size of an atom or the size of an ion. Now, ionization energy. What is ionization energy? It is the energy required to remove an electron from a shell. Now, this ionization energy, for example, you have something like sodium. We know that sodium is 11. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So ionization energy is the energy required to remove this valency electron. Energy required to remove this electron so that this sodium can become an ion. Now, if you remove this electron, this sodium will be ionized. It will no longer be this. It will not be sodium this. It will no longer be a neutral atom. It will not be an ion. So the energy required to remove an electron from its shell is what we refer to as ionization energy. The energy required to remove an electron from its shell in order to form an ion, we refer to it as ionization energy. Now, down the group, ionization energy decreases. Why? Due to increase in atomic size, but across the period, it increases due to increase in the nuclear charge. Now, we look at electron affinity. Electron affinity is energy release to form a gaseous negative ion. Energy release to form a gaseous negative ion. Now, this electron affinity, it decreases down the group due to larger atomic radii and increases across the period due to smaller atomic radii. That is to tell you that it is directly proportional to atomic size or ionic size. So, electron affinity is energy released when an atom gains a negative ion. Then electronegativity. Electronegativity simply means the ability to attract electrons. Elements that have the ability to attract electrons to themselves. For example, sodium has less electronegativity because it tends to easily give away electrons. Basically, elements between group 1, group 2, and group 3, they are more electropositive. In other words, they give out electrons. But elements between group 4 to group 7, they are more electronegative because they tend to attract electrons to themselves. So this electronegativity down the group, it decreases, and across the period, it increases. So across the period from group 1 to group 0, it increases, but down the group, it decreases. Okay, so let's look at some of the past questions on periodic table. The first question says, which of the following has the highest ionization energy? Now look at these elements. One thing you will discover is that these elements are all in the same group. And ionization energy increases across the group, across the period, but decreases down the group. So, since ionization energy decreases down the group, what will be the answer to the question? Now, first of all, you arrange them. Lithium comes first before sodium. Sodium comes before potassium. So, since ionization energy decreases down the group, that means this person's ionization energy will be more than this, and this person's own will be more than this. So, ionization energy decreases down the group. That means the one with the highest ionization energy will be this person. Number 2, elements in periodic table are arranged according to Basically, elements in periodic table are arranged according to atomic number. The question had other options like atomic masses, atomic number, relative molecular mass, relative atomic mass. It is arranged according to their what? Atomic number. Now, elements in the same group have dash. Number of shells, number of valency shells. Oh God. Now, elements in the same group have dash. Number of shells, number of valency electrons, atomic number, atomic mass. Elements in the same group, they have the same number of valency electrons, while elements in the same period have the same number of shells. Okay, so we've come to the end of the class for today. Thank you for watching. Please do well to subscribe to our channel and also invite your friends to do the same. Thank you and bye.